When you look at a swinging pendulum, or maybe a vibrating guitar string, or even a simple spring bouncing up and down, have you ever wondered what they all have in common? Their motions seem kind of complex, right? But it turns out they all share this beautiful and really simple secret. The answer is just so elegant, and it all comes down to one perfect shape. So let's dive in and uncover this hidden connection together.
Everywhere you look, things are in motion. And a lot of that motion is this rhythmic, repeating back and forth movement that we call oscillation. It's like a fundamental pattern in nature, but how do we even begin to describe it in a way that actually makes sense?
So what is it? What's the single, elegant idea that ties all of these seemingly different things together? What's the core concept that unites them?
Well, to find the answer, we have to look somewhere you might not expect. We're not going to stare at the complicated back and forth of a spring, but it's something much, much simpler, something perfect.
That's it, a circle. The big secret to understanding all this crazy oscillating motion is a simple, perfect circle. Now, I know that might sound a little weird, but trust me, this is one of those amazing aha moments in physics that just completely changes how you see the world.
Okay, picture this. You tie a ball to a string, and you start swinging it in a perfect circle at a steady speed. Now imagine you shine a bright light from the side and look at the ball's shadow on a wall behind it. While the ball is going round and round, what's its shadow doing? It's just gliding back and forth, left and right, in a perfectly straight line. And that simple observation, that's the key to everything.
And boom, that's the official definition right there. The movement of that shadow is what physicists call simple harmonic motion, or SHM for short. It is literally the one-dimensional shadow of an object moving in a perfect two-dimensional circle. So the big takeaway here is that these two motions, they are totally fundamentally linked.
So now that we've got this really powerful visual in our heads, we can actually use it to build a mathematical language, one that lets us describe this motion with incredible precision.
And this is where the magic really starts to happen. You see here, we've got a particle p going around the circle, and its shadow, p prime, is just moving back and forth along the x-axis. And with just a little bit of high school trig, we can figure out exactly where that shadow is at any moment in time. All we need is the angle and the radius of that circle. It's that simple. This whole analogy lets us create a direct translation, kind of like a dictionary between the language of circles and the language of waves. So the circle's radius? Well, that becomes the shadow's amplitude, how far it can possibly go from the center. The speed the ball is rotating, its angular speed, that becomes the angular frequency for the shadow, telling us how fast it's oscillating. And that starting angle on the circle, that's just the phase, which tells us where the shadow was when we started the clock. And all of that translates into this one beautiful, elegant equation. This formula. This is the heart and soul of simple harmonic motion. I know it might look a little intimidating, but it's really just our circle analogy written down in the language of math. It tells us the exact position x of our shadow at any given time, t.
So let's just quickly break it down. A is the amplitude, that's how far from the center the shadow moves. Omega, that OS symbol, is the angular frequency, it tells us how fast it's wiggling back and forth. And phi, or phi, that's the phase constant. It just sets the starting position of the wave when we hit go on our stopwatch.
But there's more to an object story than just where it is. What about its speed, its acceleration? Turns out our friendly circle and shadow analogy helps us understand that too. So just think about it for a second. As that shadow is sliding back and forth, is it moving at a constant speed, or is it speeding up and slowing down? And if so, where would it be moving the absolute fastest? And the answer is right smack in the middle. Take a look at the diagram. When the ball on the string is at the very top or bottom of its circle, its own velocity is purely horizontal. That means its shadow is absolutely flying as it zips through that center point. And then what happens at the ends of the path? Well, it has to stop for a split second to turn around, right? So its velocity there is 0. This slide shows the whole dance perfectly. Okay, follow me here. Look at the top graph for position. When the position hits a peak, its maximum distance, look straight down to the velocity graph. Bam! It's crossing 0. And the acceleration on the bottom, it's hitting its most negative point. These three things are always in this beautiful rhythmic dance, perfectly out of sync with each other. Now this is the final and maybe most important piece of the puzzle. The acceleration, and that means the net force, is always pulling the object back towards the center, back to its equilibrium position. When the shadow is way out on the right, the force yanks it to the left. When it's on the left, the force pulls it to the right.
This is the restoring force that keeps the whole oscillation going.
All right, that's enough theory for now. Let's get our hands dirty and see how this amazing equation actually works with a real calculation from our source material.
Okay, here's our problem. We've got an object, and its oscillation is described by this exact formula. Right away, we can see its amplitude is 5 meters, its angular frequency is 2 pi, and it has a certain starting phase. So the question is, where is this thing? Exactly, after 1.5 seconds have passed.
Let's walk through it. First, we just plug in our time, 1.5 seconds for t. Pretty simple. Then we do the math inside the cosine function to simplify that angle. Next up, we punch that into our calculator to find the cosine of that angle. And for the final step, we multiply that result by the amplitude, which was 5, and we get our answer, negative 3.535 meters. So at that exact instant, the object is on the left side of the center point.
And we don't have to stop there. If we use the velocity equation, which is just the derivative of our position equation, we can find its speed at that exact same moment, and it's moving at a pretty quick 22 meters per second.
And what about its acceleration? Well, we take the derivative again, and we find it's accelerating at a whopping 140 meters per second squared, being pulled hard back towards the middle. You see? This one formula gives us a complete snapshot of the object's entire state of motion at any point in time. It's incredibly powerful.
Okay, so let's zoom back out for a second. Why do we care so much about this simple analogy of a shadow? Why does it matter?
It matters because this is not just some neat little trick for your physics class. This is one of the most fundamental, most essential patterns in the entire universe. Seriously, understanding the shadow of a circle is the key to understanding how radio waves travel, how light works, how sound propagates, and even how atoms vibrate. It is everywhere.
So the next time you see something bouncing or swinging or vibrating, I want you to ask yourself, where's the hidden circle? Now that you know how to see its shadow, where else in the world, or hey, even the universe, are you going to find this beautiful, simple pattern playing out?